A beam of light has three wavelengths: 4144 angstroms, 4972 angstroms, and 6216 angstroms, with a total intensity of 3.6 into 10 to the power minus 3 watt per meter square, equally distributed amongst the three wavelengths. The beam falls normally on an area of 1 cm square of a clean metallic surface of work function 2.3 electron volt. Assume that there is no loss of light by reflection and that each energetically capable photon ejects 1 electron. Calculate the number of photoelectrons liberated in 2 seconds. So for photoelectrons to be liberated, we need energy of photon to be greater than or equal to the work function of the metal. So the energy of photon is given by the Planck's constant into the speed of light divided by the wavelength of the photon. This must be greater than the work function. So we have 6.6 into 10 to the power minus 34, which is Planck's constant, into 3 into 10 to the power 8, which is the speed of light, divided by lambda must be greater than or equal to 2.3 electron volts, or 2.3 into the standard electronic charge, which is 1.6 into 10 to the minus 19. This gives us that lambda must be less than or equal to approximately 5400 angstroms. Therefore, only the first two wavelengths would release photoelectrons. So now, what is the total amount of energy from each wavelength that is impinging on the metal? We have total energy is equal to total intensity, that is 3.6 into 10 to the power minus 3, divided by 3, since we are only considering each wavelength, into the surface area, which is 10 to the minus 4 square meters, and hence energy is equal to 2.4 into 10 to the power minus 7 joules. Now n photons carry this much energy. N into hc by lambda is equal to 2.4 into 10 to the power minus 7. So, or we have n is equal to lambda into 2.4 into 10 to the power minus 7 divided by 6.6 into 10 to the minus 34 into 3 into 10 to the power 8. So now if we put lambda 1 is equal to 4144 into 10 to the power minus 10 meters, we get n1 is equal to 0.5 into 10 to the power 12 total number of photons. And similarly for lambda 2 is equal to 4972 into 10 to the power minus 10 meters, we get n2 is equal to 0.572 into 10 to the power 12 number of photons. And therefore, the answer is closest to option B, which is 1.075 into 10 to the power 12 photons.